Okay, got it. And let's see what we have here. Go back to the lectures. We have is the Gaussian quadratures. And I haven't really erased the things yet. We have the proof here, but we are going to skip the proof today. So this is what we have from the last time. We have the, so we mentioned that the Gaussian quadrature rule is used to achieve the highest degree of precision. And if we have n other points, the highest degree of precision we can get is 2n minus 1. And we create the first Gaussian quadrature rule by substituting the function fx equals to 1, fx equals to x squared and x cubed here. And because we say the Gaussian quadrature rule can achieve the highest degree of precision for 2 nodal points, and that degree of precision is 3, which means that the formula, the Gaussian quadrature rule, is exact for the polynomials that is of degree of 3 or less. So we do the substitution here, and then we solve for this for equation here. This is a system of linear equation, and then we got the C1, C2 coefficients x1 and x2. As I said, mentioned last class, if we do it for the 3 nodal points, and then if we have 3 nodal points, and we would expect that we have like 6 equations, and then to solve for 6 unknowns, and that's a lot to do. And today I'm going to introduce one thing that is how to generate the nodal points and the coefficients in a systematic way. This is related to the Legendre polynomials. Let's see. I'm going to erase some things here. You don't need to take a look at here. And I'm not going to do the things here. And I believe this note is already posted on the Canvas. And so if you want to take a look at the remarks from the last quarter, and then it's good to take a look at it, but you don't need to know so much things from this course. So first, what's the Legendre polynomials? And then I believe you have already learned this from the 104A. And we have, let's say we have a bunch of basis function, and that basis function we usually use is 1x and then x squared and then x cubed, and this is the basis functions for the polynomials. And but for the Legendre polynomials, if you go back to take a look at your that is the 104A, and then you would see what's the Legendre polynomial. Legendre polynomial is a collection of orthogonal polynomials, and that is with the you can use the Gram-Schmidt process to get such a bunch, such a set of the Legendre polynomials. And then the Legendre polynomials, what is the definition of the orthogonal? It means that, so there's an inner product or the integration, which means that, so they are orthogonal, which means that orthogonal set of function, and which means that the integration, like the 1 and then pjx and then the pkx, the integrations of the product equals to 0. This is the definitions of the orthogonal, and then j does not equals to k. And this is the definition of orthogonal. And there's some property for this set of the orthogonal function polynomials. So first, we can do some normalizations here, right? And then we require that the p and x, the n degree of the the n degree of polynomials in this set of the function, and then we require it to be monic polynomials, which means that we require the coefficients for the highest degree term is 1, and then you can do this, right? You can just like divide the polynomials and then by a factor, and then you get the function and then the highest degree term, and then with the coefficients 1. And this is some things you can do. And then we require that the Pnx is a monic polynomial of degree n. And so, and because the Px, a general any arbitrary polynomials of degree less than n, and then it can be expressed as a linear combinations of, so for any degrees less than n polynomial, and then it could be represent as a0 plus a1x and then plus a2x squared, right? And then up to the an minus n and then xn, right? And xn minus 1. And because the P and X is orthogonal to the basis function 1, the basis function x, and then it's orthogonal to the basis function x squared and to the xn minus 1. So we have this happens. This is the integrations of the any degree less than n polynomial, and then in the product with the p and x, and then it equals to 0. Does it make sense? So we don't include the xn term here because the xn terms could have some things non-zeros in the integrations itself. Does it make sense? And I want to have let you to take a look at the first few Legendre polynomials here, and this is with the 0 degree, and then it just is 1. So what you need to do to generate that Legendre polynomial is just apply the Gram-Schmidt process here. So the first polynomial is just 1. And then if you use the Gram-Schmidt process to the x, and then we get this one is the P1x. And then if you keep using the Gram-Schmidt process for the x squared, and then you get this one for the Legendre polynomial, x squared minus 1 over 3. And this is the 3rd degree polynomials in the Legendre set. This is the 4th degree one. And then you have more terms after this one, but we just list the first few Legendre polynomials here. And if you do the integrations between, do the integrations of the product of the two arbitrary functions here, and then it should equals to 1 because it should equals to 0 because they are orthogonal polynomials. And this is the Legendre polynomials. Any questions before we move on? So do you have you seen this before? The Legendre polynomials is quite familiar, right? But here we just use some things we have learned from the 104A to generate the notables. So let me remind you of something about the Legendre, the Gaussian quadrature rule. So the very important thing is this is the trapezoidal rule, and then we automatically use the notables, and then that is the end of the interval. And now the question for the Gaussian quadrature rule is to smartly choose the notables, and such that we have the least error here. So the question is that how to choose this x1 and x2. It can be anywhere, right? And then, but we want to choose it, and then such that the error could be the least, the minimum error. So here, this matters. This procedure tells us that we can choose the notables by this. So there's a theorem here, and we are not going to take a look at the theorem first. So I'm going to tell you how to choose the Gaussian notables. So for the Gaussian quadrature rule, and then we are choosing the notables. And so if we want, let's say we want n notables, right? And then what should we do? We would do this. And let's see. Am I skipping something here? Okay, good. So yes, I should. Okay, good. So then we are still working on the standard interval, and then we are going to approximate the integrals on -1 and 1 fx equals to fx dx. And so now for the things I'm going to mention here is for the interval -1 and 1. So for the Gaussian quadrature through nodal points, you will see the nodal points if we want n nodal points, and then we just need to solve this equation p and x, and then equals to 0. And so for the x, and because this is the n degree polynomial, right? And how many roots do you have? N, right? You will get n solution, and get n solutions, and they are the nodal points, and they are the n nodal points. And let's see, there's some property about this Gaussian quadrature series nodal points. And let's solve it. Let's try to solve it, right? For the first nodal points, actually no one used just one nodal points. So let's start from 2, and then the p to x, and then if we solve it, and then what do we get as the degree of 2, and then we get the square root of 3, and then negative square root 3 of 3, and when degree equals to 3, and then you will see this one can be factorized into. I'm going to use the green one to write it. So this one can be factorized as x, and then x squared, and then minus 3 over 5, right? Which means that what is the first nodal point? It's quite obvious that x equals to 0 is also the nodal points, right? x0. So this is 0. And then what is the else? The other nodal points? We have negative square root of 3, and then square root of 5, and then square root of 3, and square root of 5. If you keep doing so, and then you will see that for the Gaussian quadrature nodal points, it's symmetric about the origin. The point x equals 0, and this is the degree of 3, and then which is odd number of the odd numbers nodal points, and then you will see it definitely has the origins as the nodal point. So because it's 3 degree, and it's symmetric about the origin, and then it's automatically we have the origin as the nodal point as well. So there's one thing about the property of the nodal points. So property here, properties, and we have the nodal points on the standard interval. -1 and 1. The nodal points on the standard interval are symmetric about the with respect to the origin. And this is the things. So let's get back to the Gaussian quadrature rules. We already get the very important part, and then that is the nodal points part. And then the next part is about the coefficients, right? Usually we write the quadrature rule in this way, right? Sigma sum, and then there's coefficients here, AI, and then F evaluate at the nodal points. And then so now the question is, what is this AI? Not the artificial intelligence, sorry. This is just the coefficients. We are not going to mention some artificial intelligence in this class. Although I'm very interested in it, you can use your ChatGPT to finish some of your coding homework as well. I suggest you to do so because it's a smart way to learn something nowadays. So go back to this AI coefficients. So first, let's take a look at this. Let's take a look at what we have here. This is the theorems we want to mention. This is very important about the Gaussian quadrature rule, but I'm not going to show you the proof in this class because now I show the previous class and then they just get sleepy. And they know at the end they say, oh, this is not in the midterm. You don't need to know. Yeah. So I'm not going to mention the proof in details, but I will give you an overview of the proof, like for 1 minute. Okay, so let's go to take a look at the theorem statement here. This is very important. And so first of all, it states that, okay, this is, what is the Gaussian quadrature points? Gaussian quadrature node points, and this is the first sentence. It says that the Gaussian quadrature node points, and then this is the node points, is starting from the index 1. I'm not sure why it's just starting from 1, and sometimes the textbook use start the index starting from 0, and sometimes they use starting from 1. It's like the difference between Python and C++. But here is starting from the 1, and then we have the end of the points, and then the end of the points are just the roots of the nth Legendre polynomials. And so now you have the node points, and let's take a look at this one. Do you know what is the definition of this, the meaning of this notation here? This is just the basis function for the Lagrange interpolations, right? And I'm going to write out the definitions of this one. Some people just get confused. What's this? And so, for example, let's say, so for example, we have n equals to 3, and then what happens? We have the x1, x2, and then x3. And what's this? What's the function here? And let's say, because this is calculating for the CI, right? Let's say we are calculating for C2, and this has C2, and then it equals to -1, 1. And this product here, it's like a sigma sum, but this is the notation for the products. And so here it says J does not equal to I, which means that for here, J does not equal to 2. And then the index is from J equals to 1 to the N, and then N equals to 3 here. So now what's the first term? So let's say, okay, J equals to 1. We start from the J equals to 1, and then I here, I equals to 2, right? And so the first item should be x minus x1, because I'm going to replace the J with 1. And the xi here is x2 minus x1. And the next function, the next component in this product, it should be, so J equals to 1, and then we increase 1 here, and then it should be J equals to 2, right? But for here, J cannot equals to I, so which means that J does not equals to 2 here. So we skip the J equals to 2, and then we go up increase the index by 1, and then we go to the J equals to 3. So the next item should be J equals to 3, and then we get x minus x3, and then here I equals to J, I equals to 2, and then this one, and then dx. And this is how we calculate the C2 for the samples n equals to 3. Any question here? How to read this index here? We skip the items where the J equals to 2, because J cannot be the I value, and then the I value here is 2. And this is how we calculate it. So this is the coefficients in the quadrature rule, and this is the Gaussian quadrature rule here. We have the actually I'm going to write the things not in this way. because this is the theorem statement. So for the integrations, right? For the integration -1 and 1 and then fx dx, we are going to approximate this integrals with. So we have the ci here, and then we have the sigma sum I equals to 1 and then to the n if we are starting the index with 1. And then we have the ci here and then fxi. And the xi is so far is from the root of the n Legendre polynomials. And then the ci is calculated in this way. Does that make sense? And this is the quadrature rule, Gaussian quadrature rule. Here, the information unit is ci here and the xi is from here. Does that make sense? Any questions so far? And then the next part is stating that about the degree of precision of the Gaussian quadrature rule. So here it says, if the px is any polynomial of the degree less than 2n, which means that the most degree we can achieve, it should be 2n minus 1. And if this px is any polynomial of degree less than 2n, and then we can say the formula is exact. And this is the statement, which means that it achieved the highest degree, degree of precisions. And if you take a look at the proof, I have you can take a look at the proof in the post-it notes, lecture notes. And I just briefly mentioned the proof here, the structure of the proof here. So the first part is to prove the formula is exact for the polynomial. This is the basic situations. And then it just proves that this polynomial is exact for the px with degree less than n. And then based on this, because you can see we are proving the precision is 2n minus 1, right? And then now the basic case is that we want to prove that the polynomial is exact for the degree of the function, which is less than n. And then now there's another version, and then that version is based on the basic versions. And then we are going to prove that the formula is exact. So we are going to prove that, so not going to prove, just briefly mention that. So in the proof, so first you are going to prove that formula is exact for the basic case. And then this is a step 1 and a step 2. And then it's to use the basic case to prove the formula is exact for the degree for the function, the polynomial, which has the degree that is less than 2n minus 1 or equals to 2n minus 1, and it's also except for the n degree or bigger than n degree. And this is the case. This is the proof, divided into 2 parts. And then the first one is to prove the basic part, and then the second one is to reduce these things to the basics part. To use some technique here, that is something you have heard before, but it's in the linear algebra things. And it's, let me see, it's the polynomials divisions here. And I'm not going to prove it in details. And then there's some things related to here. So if you go into the proof on the lecture notes, and then you will see the lecture note is using the polynomial divisions here to reduce the advanced case to the basic case. And I'm not going to talk this into details. It takes 5 hours to prove it. Questions?
Is this like a different version of like, are we proving the same thing we proved last class with that like contradiction proof, or is this like a different theorem?
It's just one thing, but it's just transitions.
So okay, so last class we proved it was like a similar theorem.
Oh, the similar things, right?
Yeah, we use like proof by contradiction. Is this like this? Are we proving the same thing? Just in a
No,
different way?
not the same things.
Okay.
So I'm going to talk about this. Okay. So I'm going to mention this in details. So there's the connections between the last class and this class. So for this one, so it says this is the 3-1, right? And then this one, it says that this is the general quadratus rule, not about the Gaussian quadratus rule. So any quadratus rule from the interpolation of polynomial, and then it has this format. It's the AJ and the FXJ, right? And then doing the Stiglitz sum. And then it could be a trapezoidal rule. It could be Simpson's rule, right? But you can create any quadratus you like, and then you can put the nodal points anywhere, right? But people find out that no matter how you put the nodal points, no matter how your coefficients looks like, the highest degree of precision you can achieve is 2n minus 1. Does that make sense with n nodal points? So no matter how you put the nodal points, no matter how you choose your coefficients, the highest degree of precision you can get from the quadratus rule with n nodal points is 2n minus 1. And this is the things this theorem is claiming. Does that make sense? So here, what we are going to talk about here in today's theorem. So this theorem says a node. Proof is not a problem. Understanding what is the theorem is stating is very important. So here, for this theorem, it's just saying, okay, now we get one quadratus rule. It can achieve the highest degree of precision we can get. So in the theorem 1, it says we can achieve, maybe we can achieve the 2n minus 1 degree of precision, right? This is something maybe person A find out in 19th century, and then later on, and then someone in 20th century, and then he found out that okay, maybe we can achieve the highest degree of precision with such a quadratus rule. And he found out this quadratus rule, we can achieve the 2n minus 1 precisions. Does that make sense? So first people found out that maybe highest degree of precision we can achieve is 2n minus 1. And later on, someone just find out that we can achieve that 2n minus 1 degree of precision with Gaussian quadratus rule. And what's Gaussian quadratus rule? We can get the nodal points in this way, and then we can get the coefficients in this way. Does it make sense? The difference between the theorem 1 and theorem 2. The theorem 1 should be the first things people found out. The second thing is the people want to try out to create such a quadratus rule to achieve the highest degree of precision. Questions? So people just like create something to satisfy it. It's like someone proved that there's another planet outside the Earth, and then that is the first thing. They say there's a planet because there's some evidence here, and then later on people just find out, oh, there's the Mars, and then there's another planets outside the Earth, and then they actually found that one. So that is total different things. Okay. Any questions about the theorem statement? I'm not going to prove it. Proof is not interesting enough. And then we are going to go to the calculations, computations example. We are going to make use of these rules to get the approximations. And maybe in the midterm exams, I'm going to ask you to apply the rules, and then also maybe ask you to just ask you to apply the rules. Okay, good. So this is a standard. I just say we just need to solve the Legendre polynomials to get the nodal points, and then this is the nodal points on the interval -1 and 1, and then now we're going to use this nodal points here to get the approximation of this interval. And we need to notice that the n equals to 3 for this problem. And that is the red color area I mark are there. So here the general things we need to do is just to get the coefficients and then fxi, and then times fxi, and then do the schema sum. So what we have here is we have this. We got this. We have the so for the very first point, the first point is the 0.717 something, right? And then I'm going to plot in what's this part? This part is just the, this is the fx function, right? And then we are going to plot in the fx at the 0.71745 something. And this is the f function evaluated at this point. And then what's this things? This is the rounding off for the coefficient. And then this is the value here. This is the coefficient CI. This is the fxi. And next, and then we have the node points. And then why this is cosine 0? This is because this is the function f evaluated at 0. And if you take a look at this is the node points, the middle node points for the 3 node points here. And if you plug in 0 to this function, and then the exponentials 0 is just 1. So this is 1 times cosine 0. Does that make sense? So this is the f functions evaluated at 0. And what's this? This is the coefficient for the node point 0. And that is the 0.88 something, and then it's doing some rounding off here. And for this one, is the last node point. Last node point is negative 0.771. And then do the plotting. This is the fxi part. And this is the coefficient part, the rounding off part, rounding off value up to for this one. And that's the things. And you do the summation, and then that's at the end you would get the approximations value. Which is very good, the approximations. We just use 3 node points, but the error is less than the 10 to the -5. So you could say is quite accurate results. Gaussian's quadrature rule, remember this, it can achieve the highest degree of precision. And this is the Gaussian quadrature rule. And let's scroll down to take a look what we have here. So this one is the, once again, there's the question here. How could we do the, what can we do if this is an arbitrary interval here, A and B? So we just mentioned that the Gaussian quadrature rule points here, all these points are corresponding to the interval -1 to 1. So what should we do if the interval is A and B? And then we need to do some variable transformations here. And that variable transformations is defined in this way. We are going to transform the interval A and B to the -1 and 1 by the change of variables below here. And this is the, if you are going to change the x to the t, and then we are going to use this one. And then if you are going to change the t to the x, and then this is the 1, they are equivalent. And this is the formula. And then why do we have this? And then you can take a look at what we have here. And that's the graph we have. So we have the interval here is -1 and 1, and then we want to change the A and B to the -1 and 1. And if you take a look, if we connect the point A -1 and then B 1, and then you will see actually the A is mapping to -1, and then this value is mapping to here, this value is mapping to here, and the B value is mapping to 1. And we create bijections between the A and B, AB interval and -1 and 1 interval. Does it make sense? It's a bijection map. So which means that for one point any points on the interval -1, and then you can find a unique points in the interval A and B. And then if you have a point and the interval 1 A and B, and then you will find a unique point, corresponding point in the -1 and 1 interval. Does it make sense? If you take a look at this picture and then you connect the point A -1 and then B 1 here, and then you write down the function by the slow point slow form, and then that's the mapping function. Does it make sense how we get the mapping functions? It's just like connect the points here and then get the functions by the slow point form. And any forms you like. So you write down the functions of this line. And so now if we have the change of variable here, and we got the functions, integrations, this is the fx function, and then equations on the arbitrary interval A and B. And we are going to change the x with that change of variable. And the x equals to b minus a, and then times t, and then plus b plus a, and then divided by 2. And this is replace it with the x with that expression. So this is from here. We just have the x. I'm going to calculate all the things here, and then would give you the summations below, because I know some of the people just forget what we have from the calculus class, how to do the change of variable. So now I'm going to do it step by step here. So let's say we have an interval A and B, and then dx. And then we are going to, so first let's keep writing the limit part here at this moment. And then here we are just going to substitute the x. We are going to use this right-hand side expressions here, x equals to the expressions function of t. And then we are going to replace the things with 1/2, and then b minus a, and then t, and then plus a plus b. And then this is the things inside the parentheses. And then what about the dx? So dx, it should be equals to the dt, and then it's just the change of variables. So this is the function dx dt. Does it make sense? What is the dx dt? This notation is just the derivative. The derivative of this function. Does it make sense? Or if you calculate the derivative, and then what's it? That is the derivative of x regarding the variable t. So what's this? In case you forget what's the definition of this one, this is the derivative of x regarding the variables t, variable t. And then what's the dx? This is the notation for the derivative. And then dx dt, you can view it as the small change in x, small change in t. Does it make sense? So now what is the dx dt? The derivative. The derivative is just the 1/2, and then b minus a. So here we have 1/2 b minus a, and then dt. And because the change of variable, we change the variable from x to t, and then now because this is a bijection between the -1 and 1, and then the interval a and b, we have such a bijections here. We are mapping -1 to here. We are mapping the 1 to here, and then the things in between mapping to the interval a and b. And so we are changing the integrations limit as well, and then we have the -1 and 1. And that's the things we have the formula here. Those things, x is changed to this expressions, and then we have this one from the change of the dx. Now I'm going to apply this to the one concrete example here, and that is the we are changing. Oh, there's a lot of calculation here. I'm going to just mention the quadratic points for the first for the n equals to 2, and then you can read the examples later on for the n equals to 3. So here what we did, so let's take a look at here. We have this calculation here. It's just the a and b, right? And then we have the 1 and 3 and the fx dx, and then this is corresponding to here. And what I did here is just I plug in what I have in the formula, and then it's changing to -1 and 1. And then what's the b minus a? B minus a is just a 3 minus 1. So I got 2. And then so that I have 2t here, and then plus the 3 plus 1, and then I got 4 here divided by 2. So this part is corresponding to this part. And for the b minus a divided by 2, and then I have 3 minus 1 divided by 2, and then dt. So this is what I have at the end. And we are applying the Gaussian quadratic rule to this function. Which means that, so let's see, for this function, and this is a function about t, right? And so at the end, we need to get the nodal points from the, what's the nodal points here for the 2, n equals to 2. N equals to 2, we have the 0.57 something, negative 0.57 something, and then the coefficient is just 1, 1. So let's see how we apply the Gaussian quadratic rule to these functions here. So the T1, I just copy down the nodal points T1 and then T2. Let's T1 and C2. This is the corresponding coefficients there. And so I'm going to plug in the T1 to here. So this is the Gaussian quadratic rule, C1 and then F evaluate at the first nodal points, and then but here we have the plus 2 here for this function. And then this is C2F and then T2 plus 2 here for this function. And this is how I apply the things, and that is 1 times the nodal points plus 2, and then 1 times the nodal point plus 2. Does it make sense? So I just replace, because this is integration about t, so I replace the t with the nodal points. But don't forget that we have the plus 2 here. This is easy to forget to apply. If you take a look at the examples for the nodal points 3, and then you will see something similar to here. But for this one, the change of variable are the same. The change of variable are the same. First we do the change of variable, and then we get this function. But now we got the difference C1, C2, and C3, and then we have T1, T2, T3 here, and they are the same. The rest of things are the same. But you need to take a look at the table, look into the table, and then get the corresponding value. And then that's it. You don't need to, if I ask you to solve the Legendre polynomial to get the nodal points, and then you need to solve it. Otherwise, you just need to look into the table to get the values, to get the nodal values and then and the corresponding coefficients. Most of the time, the people just use the table, not solve the Legendre polynomials at the very beginning. So I'm going to give you some remark here, and this is the connections between the Gaussian quadratic rule and then the Crenshaw-Curtis quadratic rule. Crenshaw-Curtis quadratic rule is not required. This is so advanced topic, that Crenshaw-Curtis quadratic rule, and I'm not using it frequently, so I'm not going to test you on that part, the Crenshaw one. Not a lot of people are mentioning the Crenshaw's frequently. So let's compare the Gaussian quadratic rule. Once again, for the Gaussian quadratic rule, it's still the it gives you the highest possible degree of precisions. But I just mentioned there's one disaster when we do the interpolations, and then there's some oscillations on the interval where it is close to the why this is not here? Well, let me see. This is not the post-it notes. So I mentioned in the last class that in the, let me see, do I include here? I believe I just show you the Google page. But if you take a look at the post-it notes, and then I mentioned here, that is a Rongers phenomenon, and then I show you last time, and then if we keep increasing the nodal points, and then the interpolations, it could be oscillating close to the end of the nodal point of the interval, right? Do you remember this? And then it's get oscillating. So for the Gaussian quadrature group, it has the same problem. When we keep increasing the nodal points, and then maybe the error is not going to 0, and then it could be increasing to infinity. So that's why some people would choose the Crenshaw-Curtis sometimes because the function is so weird, and then you need to have the Crenshaw-Curtis quadratures to help out there. Sometimes you need to get a better approximations at the boundary, and then that's why people need the Crenshaw-Curtis sometimes. But a lot of time people just use the Gaussian quadrature rule because it has the highest degree of precision. If the function is the integrations for the functions here, if the function here is quite smooth, and then people prefer to use the Gaussian quadratures. If the function is quite weird, and then at the end, and then people would just go for the Crenshaw-Curtis. And that's the things. And then there's some not very important property about the Gaussian quadratures coefficients. So Gaussian quadratures coefficients is always positive. And then also we use the weight equals to 1 here throughout this course. And then this theorem, this property is saying that the summation of the coefficients, and then it equals to the integration of the weight function. And let me see. This is not quite important, and then I'm going to skip this part. And so that's all the things. You just need to know how to compute the Gaussian quadrature for the concrete example. And maybe sometimes it will also ask you to solve the Legendre polynomial to get the Gaussian quadrature points, nodal points. And that's it. Any questions? And then you can come over here to ask me.
Thank you.
他的意思是说，第一个是告诉你，任何的 quadrature rule 它只能达到 2n 减1的最高的精度，然后后来人们就创造了一个 quadrature rule 去满足最高精度。
哦，所以第一个是 prove 它只能达到2n减1，
对，
后面
就是任何的 quadrature rule。
后面是
创造了一个，
然后达到2n减1。
对
，OK， 好的。
我确定一下啊，就是咱们这周不是讲了高盛高盛，对吧？咱们讲高盛高盛，上周我没来，然后上周讲的是这个科恩少。
对，不重要，不考。
然后这周的话讲的就这周是讲了这个 trapezoid rule 和 Simpson rule， 除了这个之外还有 composite。
对对。
composite 是这周讲的，这个。
这周讲的呀，我都是放在对应的那个点上的。
OK， 好的，谢谢。
啊 ，OK，没事。